So when we think rotational, you want to think of something that sits on an axis and that spins. And so when we calculate rotational movement, we're going to thinking the angles that it's moving. So we're going to think angles and rotations compared to what those angles look like as it moves. That would be the rotational. So then what's the difference? Here's the picture I was talking about. The difference is the two things that are happening to the earth. The rotational movement is this guy. He does that continually. If he didn't, we would all burn up or freeze, depending on what side. And he does this continually. Again, we need that movement in order to make the world go round, literally, right? We need that movement for everything to work the way it does. If we didn't have it, we would not have life. I mean, we would not have life on earth if that didn't work, right? Things would fry or freeze, right? We've got to have that continual movement. And so it actually does both. It has rotational and it has circular. So let's look at what we talked about. So we're going to go back to very beginning when we talked about displacement. All right. This is a picture. It's hard to imagine. I don't know if you've ever been on one, but I have. These are the little merry-go-rounds, like at a park, right? Where you sit and there's a spinner in the middle or someone spins you, right? And so if I were to talk about displacement, there's probably not a whole lot of displacement going on, right? Displacement means from my original path. So if we're on this original path and we move and we go back to where we started from, we actually have a zero displacement. But we've certainly traveled. Our bodies tell us that something has happened, right? She is going along this little outside path and she is spinning. Now, we put it on what's called a polar coordinate system. That should make sense to you if you've ever seen a globe. All right, polar coordinate kind of looks for globe, we actually stretch it out and we do some polar mapping, right? But polar coordinates actually look at it differently. They look at how far we've moved angularly and then how far we are from the center. And those two things determine how far I move. If you've ever been on a merry-go-round, like the horses and all, if you're on the outside horse, you travel more than the guy that's really close to the center. Right, well, because the radius is different, right? And so clearly I'm going to do that. If you've ever watched racers, have you ever noticed that on a circular or oval, they start at different points, but the finish line is at the same? Why would that be? Well, because the outside circle's gonna be bigger, right? And so they adjust those so that they have the same distance once they've started that lap, right? And so that makes sense to us, and it should make sense that this polar coordinate system is going to give you a theta. This should look familiar. That represents an angle in radians. And then it gives you a radius, how far away I am from center. And we're going to use those two things to calculate how far I've actually traveled. All right. So in this particular scenario, they've given us a 45 degree. That is pi over 4. I am going to say, I mean, for those of you that have done trig with me and unit circle with me, that should be very familiar. For those that have not, it's okay, because when I teach this, I'm going to teach it compared to an entire circle of a 360 so that you don't have to worry about those conversions that we haven't really done yet in our math world. But that would be how far she's traveled in radians, pi over 4. Remember, that's just another representation of angles. Degrees, radians. Those are two ways to represent angles. However, when we talk about measuring, like if I were to stretch it out and measure it, we're going to use radians for that. We're not going to use degrees, all right? And then 1.4, that's how far away she is from center. And so that's what we would use to figure out how far she travels. All right, so let's talk about position and displacement. When it comes to angular displacement, radius is constant. We should all know that, all right? By definition of a circle, right? The radius doesn't change or it would not be a circle, right? Angular displacement, that's going to be that delta. That means what? Delta means what when we see it? Change. The change in the theta. So theta is going to start here at 0, just like when we did movement. Standard movement is counterclockwise. We've already talked about that. And so positive movement is going to assume this direction. Negative movement is going to assume that direction. The amount of rotation or change in the angle is what we're looking for. CCW, that means counterclockwise is positive direction, by the way. We just don't like to write it all out. So counterclockwise, to your perspective, is going to be positive, and clockwise is going to be negative, right? All right, the relationship between the distance traveled and the angular distance. This is labeled S. S represents that arc length, okay? That is your radius. That is your theta. Theta is your angle in radians. I will say, when I teach this and they give it to you as an angle, I teach it as I have an angle out of a whole circle, which is 360, and then we're going to multiply by 2 pi to convert it to radians. So you don't have to worry about the conversion, but this is always in radians, all right? So we're just going to take our radius and we're going to multiply it by our angle in radians, and that will be how far we've traveled on that arc, right? If you were sitting on that merry-go-round, that's how far you would have gone. So S is the arc length, the distance you have traveled. R is the radius, and theta represents the angular distance in radians, all right? So for that formula, that's what you're going to be looking for. Questions? So you could go, so I'm going to show you both ways, right? We have radius times theta. That's going to be how far we go, pretty much. However, they didn't actually give us a theta. They gave us the word revolution, okay? So revolution is literally a circle. A revolution means you went in a circle. So how many times did they go in a circle? Well, 7.3 times, right? So I teach this a little differently. Yes, you can certainly do r times theta and then figure out your theta in revolutions, all right? But here's what I want you to think about. I want you to tell me what the formula is for the circumference of a circle. So the circumference of the circle is 2 times pi times r. Everybody agree with that? That would be going around in a circle. Yes? So if I were to look at this, one circle for this guy, if my radius is 1.4, would be 2 pi times 1.4. Everybody agree with that? So then all you have to do is multiply by how many times you did that. How many circles? Well, they told me in the problem. How many circles did I go? I went 7.3. Every revolution is 2 pi, okay? So if you take the circle, 2 pi r, and you multiply it by how many times you went around the circle, you will have your distance traveled, all right? So go ahead and calculate your distance traveled. In your calculator, this is all multiplication. So you can say 7.2 times 2 times, you're going to have to do a shift key here, depending on your calculator. Mine is actually right above my exponent mark, my little caret top. So we'll have to probably do a second depending on your calculator. Mine is the second and that key. That will give you your pi. And then you're going to multiply that times 1.4. So you can do it all in your calculator. It's multiplication, and you can hit the answer at the end. Significant digits. There we go. So 2 significant digits gives me 64 meters. Why do I know that it's meters? And why would there be units? I'm asking for a distance traveled. Significant digits require units. Meters is how far they told me. It's going to be based on that radius. Yes. So for this one, they've given you your radius. They've given you your rotation. So we're going to talk angular velocity first here. Angular velocity is the change in the angle per the unit of time. That makes sense. What does velocity mean? Velocity, when we thought about it way back when we're just, a train traveling along, we would look at the distance traveled divided by the time, right? Angular velocity is the angle traveled by the time. That's all that they are talking about there. So we're gonna introduce some more Greek for those of you that like this part. I do. Omega. This is the lowercase omega. Right, so angular velocity. So omega is the average angular velocity. So omega, it makes sense. Don't let, that's why I pointed out actually the Greek letters. Don't let all of those confuse you. They are just variables. The omega is the average angular velocity. That little line over it means average. We used that actually with all of our averages way at the beginning. We had that little line to say average. And then at the top, a delta, that's your capital letter delta, change in angles, that's what the theta means. divided by the change in time. So basically what you're saying is, if you are standing in the middle of something and spinning, we're going to say, well, what's the angular, how many angles did you go through? We're going to do it in radians, but how did you go through here? And then we're going to divide that by how long it took you to do it. And there's your angular movement. Okay, there's your angular movement. And of course we know delta time, that's change in time. So angular displacement, remember this is, we're going to look at how far we've displaced angular. So it's a little bit different than if you think about traveling on the edge there. All right, so angular speed and velocity is also often given radians per second is typically your standard unit of measure for this. Radians per second. Common usage is typically revolutions per unit of time, such as RPM. That should look like a familiar term to us. What does that look like? Where have we seen that before? So keep in mind, when it's revolutions per minute, then every single revolution is one circle. So we're going to do the same conversion. We're going to take the revolutions and multiply it by 2 pi. 2 pi is one circle. All right. If they don't have it that way, we can convert it. If they give us revolutions, we can convert it. If we have it one way and go to revolutions, we can convert the other direction, right? So you have to be thinking a revolution is one circle as we go through this. All right, the merry-go-round that's previously described in earlier in the chapter rotates clockwise. Is that a positive or negative movement based on what I've said? That is a negative movement. 46.7 degrees in 40.45. That point is important. What's the angular velocity of the merry-go-round in radians per second and rotations or revolutions per minute? All right, so I do this a little bit different because I look at it as part of a circle. So when I think of 46.7 degrees, I'm going to think that what part of a circle is that? So I actually set up a ratio. I say it's negative movement, 46.7. How much is one circle in degrees? 360. So since they gave it to me in degrees, I'm going to do that. I'm going to say I have 46.7 out of 360 degrees. It doesn't matter if it's bigger than 360. That's just going to be more, right? And then I'm going to take that and I'm going to divide it by how much time, right? So 0.45, that's what I'm dividing by. But they specifically said, hey, I don't want degrees. I want radians. And so a whole circle in a radian is 2 pi. So we're just going to convert to 2 pi with that multiplication. Now in your calculator, you do want to make sure that you don't put any parentheses around this 0.45. It will do order of operations, all right? So it will do negative 46.7 divided by 360 divided by 0.45 times 2 pi, all correctly. But if you are more comfortable saying, I want to enter here and get an answer, and then I want to divide by 0.5, and then I want to multiply by 2 pi, you can. But you should get the same thing. We are going to be to how many decimal places? Well, how many significant digits? 2. So you should have gotten what? Negative 1.8. Yes? Radians per second. If you didn't, check your calculator. So here's how I do this. All right? I'm going to take that same percentage of the circle. I'm going to take the same percentage of the circle. And technically, dividing by that 0.45, I am already in revolutions per something. What am I in revolutions per right now? Per second. What are revolutions per in this? Minute, right? Minute. So this is the only reason I write it this way. So I am going to actually write this division as a multiplication. How do I write a division as a multiplication? How do I do that? Multiply by the reciprocal. So I'm going to actually just write it like this so that I can very easily see how to convert this to minutes. This will tell me how many revolutions per second I am doing because that's all I've done. A circle and how many times it took me to go in a circle, right? But I need to convert this to minutes. If my seconds is in the denominator, how do I convert it? What needs to go in the numerator? If my seconds the seconds need to go in the numerator at 60 seconds per 1 minute. So the only reason I mean, you could write the other one that way too if you want to. But the reason I do this one over is so your conversion makes sense. And this will be revolutions now per minute. So how many revolutions per minute? And again, this is still negative because you are telling me direction here. Velocity and speed. So velocity is the distance over time. For angular motion, we have that velocity is that s over t. We could replace it. Angular displacement is r times theta. So if we already know our angular movement, this is saying all you have to do is take it. Remember what was omega? So they've just kind of gone through the process. They've said, well, I'm going to take all this. I end up with this velocity. We've already done r times theta over time. That's what we've been doing, right? If I already know that, I can actually, once I know omega, just multiply by the radius. It ends up being the same thing. So if I find my angular, right, that I've already calculated, I can just multiply by the radius to find my distance. All right, so it's like if you were to take that angular movement and spread it out across, how far did you travel, right? That's what we're doing. We're just converting it. And once you have it, once you have omega, you can multiply it by the radius and you're already there. So it's not like you have a ton more calculations that you have to do. All right, so let's look at what all these things mean. V sub t, that is the linear or tangential. Tangent is a tangent line speed. R is the radius. Omega is the angular speed in radians per second. So if it's in revolutions per minute, you are going to have to convert it, all right, to radians per second before you can multiply it by your radius. But that's what those stand for. V sub t is your linear speed. How far have you traveled linear? All right, you can use this with a tire. You can figure out your angular movement of your tire, and it will tell you how far if you've gone, right, if you know that radius. So it does have to be in radians per second, though. You need it in radians per second, so you may have to do some conversions. Just pay attention to how it was given to you. Tangential velocity. So what does this mean? The linear velocity of any point on an object in rotational or circular motion. So tangent. First, let's talk about what a tangent line is. If I were to do a circle, which that's what we're talking about. So if I were to draw a circle, and let's pretend this circle is spinning, what it's telling me, tangential velocity, is if I were to take any given point on that circle and do a tangent line. All right, so I'm going to try to draw a little tangent line. There we go. Depending on how it's rotating. So let's say this guy is rotating this direction. All right. If the object were to come off, right, what would the speed be? This is like the instantaneous, like at that specific point, at that tangent line, how fast is that object going, right? And then where would he go to? And so that's a little bit different, but you do have to think about how it would shoot off. It actually would shoot off at a perpendicular motion, which is kind of interesting, right? So if I were to draw the perfect tangent this direction, then I have this line there. And so tangential velocity, that's the linear velocity at any given point in time as you're going around it. And so that could be different depending on where you are. But it's if your object were in rotational or circular motion, what is it at that specific point in the movement? So angular velocity vector, this is kind of an interesting one. So this is called the right-hand rule of rotational motion, let's say, in one more R. It's actually called the alliterated rule. Your fingers curl in the direction of the rotation. So if I were to take this little guy here, all right, if he's rotating, I'm going to go this way because it's easier for me. If he's rotating this way, all right, my fingers are going to curl in the direction that he's spinning, all right, and then your thumb would go up. So that means the angular velocity vector would be this direction. Why does it matter? Well, if I go the other direction, the angular velocity is down. It's always going to be perpendicular to what's going on here, just which perpendicular is what you're looking for. So if you were to take your fingers and put it in the way in which it's spinning and then put your thumb up, that is the side of it that it is going to be pulling, okay? If it rotates this way, it's going to be this direction. And so you can always place your fingers as they curl in the direction of the movement, and your thumb will be pointing in the way that that angular velocity vector is pulling, okay? And so the direction on which it spins matters. You know where I feel like I would understand this the most is a ceiling fan. So ceiling fans, did you know they have two ways of moving, right? One way, if it goes one direction, it blows down, right? You can use a ceiling fan in the heat, in the winter, to actually pull that air up, right? And so you can turn it the other way and it actually goes the other direction, right? Have we ever done this with our ceiling fans? Did we know they did that, right? I'm going to use another example. Let's say a shop vac. Have we used a shop vac before? We have, right? One end of the shop vac is blowing, right? What's the other end doing? It's sucking, okay? Because the fan in there has something going, right? That way you don't even have to change the direction. You just have to actually go to the other end of it. But you have the pull of it from where that rotation is happening. It's always going to be perpendicular to the rotation, right? To the plane that is rotating. But the direction of that angular velocity is going to be, you can curl those fingers in the direction that it's going. So if it's going this way to you, you're going to see it go up. If it's going that way, you would place your fingers in the curled position and it would be down. So torque causes rotational acceleration. You have probably seen this term somewhere else before. Where have you seen the word torque? Acceleration. So when you look at your 0 to 60, you have a Kawasaki Ninja 750, 0 to 60 in 2.3 seconds. Why? Because it has high torque, right? Right? We have, grandma's, a 1988 Lincoln Town Car, probably not going to go 0 to 60 that fast, right? So how quickly it's going to get that car moving and cause that rotational acceleration, that is your torque. So when angular velocity changes, we have angular acceleration. So rotational acceleration, when the angular velocity changes, we have angular acceleration. Remember, velocity does not necessarily mean that you're accelerating, right? Velocity means that it's moving distance over time. Acceleration is when that guy changes or decelerates. You could hit the brakes, right? Angular acceleration is the rate of change of angular velocity. Rate of change, that should make sense. Let's look at the formulas they've given us. Average angular acceleration, this should look like alpha, equals the change in omega, that is my angular, over time. Change in angular velocity over the time interval. This is measured in radians per second squared. Per second squared. Remember, we're talking acceleration now. So remember, velocity is distance over time. Acceleration is distance over time, right? Because we're taking that. So that's why it's squared. How much it changes every second. Acceleration in rotational systems. Omega is oriented along the axis of rotation. The alpha also coincides with the axis of rotation. So that coincides since we're talking about dividing that by time. So those are going to go on the same vector there. All right, so angular and tangential accelerations depend on the distance a point is from the axis of the rotation. If I were to have a slingshot and I had a really short slingshot, right? I'm not going to get it to go very fast, right? If it's further out, it's going to go faster, right? If it's the same rotation, because it's having to move further in the same amount of time. So it's going to be going faster. So in this, a sub t equals alpha times r. My tangential acceleration is the a sub t. The alpha is angular acceleration in radians per second squared, and my r is my radius. The direction of this equals the tangential to the circular path at the object's position. So we were going to finish this up tomorrow, but we'll have some examples tomorrow. So take your original, take your ending, subtract your original, and then how long did it take him? How long did it take him to do that? 1.3 seconds, and that's what we're going to divide by. All right, so this is just going to be our rotations, RPM, but it's not per m. How much is per what? Rotations per second. So we're going to do rotations per second first. What are the rotations per second? We're not going to worry about significant digits until we move it across. So right now you should get something like this. Rotations per, or revolutions per second, something like that. Is that what we get? Now, they specifically want radians per second, right? Technically per second squared here. All right, so we have our revolutions per minute per second, pretty much is what we're doing. And then we need to convert it. So we have 1300 would be our significant digits, right? Because we only have 2, I think, up here somewhere, 1.3 seconds. So we're going to take 1300 when we do this one. 1300. This is revolutions per minute per second. All right. They gave us RPMs and they gave us seconds. So we actually have minutes, seconds. We're trying to get it to seconds. All right. So how do we convert it? Well, we have 2 conversions here. This is revolutions. Remember, every revolution is a complete circle. So we have to multiply our revolutions by a complete circle, but in radians. What is a complete circle in radians? 2 pi. So anytime we have revolutions per minute and they want it in radians, we have to convert with a 2 pi. That's going to convert it to radians. Now we're minutes, seconds, because they have revolutions per minute and then they divided by seconds, right? So we need to convert that minutes. All right, so how are we going to convert minutes? Well, minutes is here. I know this is a weird, but it's going to be second. So minutes will go on top. Seconds will go on bottom. So that is what our conversion is going to look like. It's going to be the negative 1300 times the 2 pi, then divided by the 60 to get the radians per second squared. Radians per second squared. In 2 significant digits for this one. What do we get? So you should get 140, technically negative because he slowed down, radians per second squared. That is the acceleration. Remember, acceleration has direction. We're slowing down, so negative 140 radians per second squared. That's the answer to the first question, radians per second squared. All right. Now remember, once we have this, if you look at our formula, that average angular acceleration, that's what this is for right here. And if we multiply it by that r, we're going to get the tangential acceleration, what that acceleration is at the end of it. So we've calculated the angular acceleration. How fast is it spinning? That's what they're asking, right? Angular acceleration. How fast is it the spinning speeding up or slowing down, right? Now we're saying what's happening if you were sitting on the tip of that blade, how fast would you be speeding up or slowing down? That's what we're asking at this point. And if you have how fast it's spinning, you just multiply him by how far away you are. You're our radius away. So we're going to take that answer that we just got, that negative 140, and we're going to multiply it by the 2.07 meters. And now we're going to be, by the way, radians per second squared. There's not a conversion that you have to do to get rid of the radians. All right. What you're doing is you're converting a rotational to a circular. So this is immediately going to be in meters per second squared when we multiply by a meter, okay? It will be in meters per second squared. And again, to two significant digits, you should get what?
380.
It's weird. All right, so insignificant digits, and it is a negative, by the way, because you are slowing down. Acceleration, that positive and negative is telling us, are we speeding up or are we slowing down? What are we doing here? So we are definitely slowing down.